Welcome to this video lesson. This video focuses on how augmented matrix can be used to solve system of equations. Before watching this video, it is helpful for you to know how lines actually work graphically and how you can solve system of equations. Let's start with a two-dimensional example. We're going to have our grid and we're going to have an equation 3x plus y is equal to 4. That's going to be our orange line, and x minus 2y is equal to 6 is going to be our blue line. And these are just sketch of the line. We're not doing exact numbers and grids for this one. Note that the main reason we solve system of equations is to find a point of intersection. And in this case, if we were to switch the two equations, if we were to change their locations, having x minus 2y is equal to 6 on top and 3x plus y is equal to 4 on the bottom, it doesn't change the two lines. The orange line will still be the orange line and the blue line will still be the blue line because they are the same equations. Note that we can also multiply or divide any of the equations by a constant value as long as we do it both to the left-hand side and the right-hand side, and the line doesn't change. The line will remain the exact same line. For example, in this case, we can label x minus 2y is equal to 6 as equation 1, multiply that by 3, and multiply every single term in there. So 3x minus 6y is equal to 18 will be our new equation, but the line will now be the pink line, which is the exact same line as the blue one, and the orange line still remains the same. You should be familiar with these two concepts if you have solved system of linear equations before, but we're going to do something new now. We're going to take the pink line's equation, that's going to be our equation 2, and the orange is going to be 3, and we're going to try replacing equation 3 with 2 minus 3. So equation 2 stays the same, 3x minus 6y is equal to 18. But for equation 3, we're going to replace it by 2 minus 3. So 3x minus 3x is equal to 0. Negative 6y minus y is negative 7y. And 18 minus 4 is 14. Let's label this as the purple line, and if we were to simplify this, it would be y is equal to negative 2. That means y is a constant value of negative 2, and if we were to draw that, we can see that it's a straight line. Note that even though we did change the line itself, the point of intersection does not change, and that is the important thing that we need to consider. We need to know that even though we are changing the line itself, the point of intersection remains the same, and we can use this method to solve for the point of intersection. To have a nice systematic way of solving for point of intersection, we use what's called the augmented matrix. Augmented matrix will be used to write our equations in a more simplified form. So we're going to have square brackets, and we're going to have two rows in this case for the two equations. Row 1 being the first equation and row 2 being the second equation. The first column is going to be the coefficients of our x values, and the second column is going to be the coefficient of our y values. If we had more variables, then we would have more columns, and if we had more equations, we would have more rows. The vertical line in the middle is going to be our equal sign, and everything to the right side, which is our constant values, are going to be written to the right hand side of it. We can do certain row operations here. We can change rows or interchange them without changing anything. As we saw, the lines remained the same if we change the equations, and equations here represent the rows. As we saw previously, we can multiply or divide the equations by a constant value, so we can do the same thing to the rows without changing the final solution. And we can finally replace rows by a multiply of itself, added or subtracted by a multiply of another row. And as you saw before, this does change the line itself, but it does not change the final solution or the point of intersection. Let's use our example above and try to solve for the intersection. So we write it in augmented matrix form with our coefficients on the left-hand side and the constant on our right-hand side. We're going to do the same operations we did above, but in matrix form. So Our first equation is going to stay the same, but our second row is going to be replaced by our row 1 minus 3 times r2. We're going to do this operation for each value in the row. So for the first row, we have value of 3. We're going to subtract that by 3 times the first value of row 2, which is 1. So 3 minus 3 times 1 will give us 0, and we'll replace our value of row 2 with 0 here. Then the second value of row 1 is 1. We're going to subtract that by 3 times the second value of row 2, which is negative 2, and we will get 7. We will write that down. And finally subtract 4 by 3 times the value of row 2, which is 4 minus 3 times 6, which will give us negative 14. Now we can use our second row to solve for value of y, because 7 is the coefficient of y and coefficient of x is now 0. So 7y is equal to negative 14. That gives us y is equal to negative 2. Now we can use the first row to solve for x. So 3 times x plus y, which is negative 2, is equal to 4. And we can rearrange this for x to get x is equal to 2. The process of reducing the values to 0 in our matrix is called row reduction. And our aim is to have enough 0 values in order to solve the other variables. So one way of doing this is to reduce it into what's called the echelon form. And this means that we want to obtain zeros on the bottom left-hand side of the matrix. So in a 2-dimension, we'll have the 1 0 in the left-hand corner. And in the 3 by 3, we will have 3 zeros in that bottom left corner. I want to mention again that this is not the only way of doing this. We can reduce it to different forms, but this is a very nice form. It's easy to get there and it's easy to solve for the variables after. Once we have it in this form for a 3-equation form, we know that using the last row, C3 times Z is equal to D3, so we can solve for Z. Then we can use the second row to find Y, and then we can use the first row to solve for X. The summary of the concepts is fast forwarded here, so if you need to pause and write any of the information, please feel free to do so. And now we're going to look at one example. Okay, in this example, we are going to have 3 equations and we're going to find the point of intersection between them, or the x value, y value, and z value for which these equations will be true. We're going to write this in matrix form, and we're going to write all the coefficients of our first equation, so 2, negative 1, 3, and then the constant on the right hand side. For the second one, our coefficient is 2 for x, negative 2 for y, and negative 5 for z, and our constant is 4. And for the third equation, the coefficients are 3, 2, and 2, and the constant is 10. The aim here is to get all the bottom left-hand corner values to be 0. That means we want to have the first value in the second row to equal to 0, and the first 2 values of the third row to equal to 0. First, we can do operations to get the first values of the second and third row to equal to 0. To get the first value of the second row to equal to 0, we have to look at the coefficients of x in the first and second row. They're both 2, so we can just subtract them by each other, and we should get our second row's first value to become 0. So we'll keep the first row to be the same, and the second row is going to be replaced by row 1 minus row 2. Then we're going to subtract 2 minus 2 to get 0, negative 1 minus negative 2 to get 1, and 3 minus negative 5 to get 8, and finally 17 minus 4 to get 13. Now we want to get the first value of the third row to equal to 0, and we can use the third row and first or second row. It doesn't really make a difference. Let's use the first row for this purpose. The coefficients of x for the first row is 2 and the third one is 3. So if we want to cancel them out, we need to find the lowest common multiple. In this case, that's 6. And to get that, we need to multiply the first row by 3 and the third one by 2. And therefore, we can subtract 3 times the first row by 2 times the third row. Here we will get 3 times 2 minus 2 times 3, which is 0. We will get 3 times negative 1 minus 2 times 2, which will give us negative 7. We will get 3 times 3 minus 2 times 2, which will give us 5. And we will get 3 times 17 minus 2 times 10, which will give us 31. Now we want to get the second value of row 3 to equal to 0, and we can use either row 1 or row 2 or the new row 2. We're going to use the new row 2 in this case, and the lowest common multiple here is 7. So we're going to multiply row 2 by 7 and add it to row 3 in order to get 0 for our second value. Note that because this is the new row 3, we're going to use double prime. We're going to use row 2, the one from last time, so that's 1 prime, and we're going to use row 3 from last time as well. So I should have put a prime here, I forgot, but there should be a prime there. So now 7 times 0 plus 0 is 0. 7 times 1 plus negative 7 is 0. 7 times 8 is 56, plus 5 is 61, and for the last one we get 91 plus 31, which is 122. Now the left bottom corner is all 0 values, so we're going to use our last row. We're going to have 61 times z is equal to 122. Divide by 61 to get z is equal to 2. Then from the second row we have 1 times y plus 8 times y is equal to 13. That's y plus 8 times 2, because z is 2, is equal to 13, and we're going to rearrange to get y is equal to negative 3. Finally, we're going to use the first row, so we're going to have 2 times x minus 1 times y plus 3 times z is equal to 17. So that's 2 times x minus y value is negative 3, plus 3 times z value, which is 2, and that's equal to 17. That gives us 2x plus 3 plus 6 is equal to 17, and we rearrange for x to get x is equal to 4. And those are our x, y, and z value. I have left you with 3 examples to try out on your own, and I will try to post a solution to these as soon as I can on a separate video. I hope that you got an idea about how you can use augmented matrix to solve system of equations, and in the next 2 videos we're going to apply them to figuring out points of intersection of planes. First we're going to do 2 planes, then we're going to focus on the intersection of 3 planes. Thank you for watching.